I'm going to talk about the interior and exterior angles of polygons. Let me start by making a drawing, and then we'll continue. So my drawing has a triangle with one side extended in a certain direction. And let me label the vertices of the triangle. And let me label the remaining point denoted by a red dot. Okay, so the angles of the triangle, I'm referring, of course, to triangle ABC. The angles of the triangle, angles BAC, angle B, and angle C. I can't say angle A because that's ambiguous, so that's why I called it angle BAC. Those three angles are referred to as the interior angles of the triangle. All right? When you extend a side, as I did in the picture, you create what's referred to as an exterior angle. Okay? So angle BAX is an exterior angle. All right? Notice that when you extend a side, you create a straight angle. So angle CAX is a straight angle, but we want to focus on the angle that's not a straight angle. And that's the one that we call an exterior angle. Okay? Angle BAX in this example. All right? Now, if you understood what I just said about interior and exterior angles, I'd like you to think about how you would prove the following. Can you prove that the exterior angle in this picture has a bigger measure than the non-adjacent interior angles of the triangle? So in other words, can you prove that angle BAX is bigger than angles B and C? Let me repeat that. Can you prove that angle BAX is bigger than angles B and C? That's what B and C are what I'm calling the non-adjacent interior angles. Okay? Angle BAC is interior, but it's adjacent to the exterior angle. Okay, so you might want to pause the video and see if you can prove that. Okay, this is just to get us thinking about interior and exterior angles. So let me show you one way that you could do that. So I hope you can see that the following is true. So the exterior angle, BAX, the measure of that plus the measure of BAC is 180 degrees. So those two angles form a straight angle, right? Furthermore, the sums of the measures of all the interior angles of the triangle also equal 180 degrees. So BAX, excuse me, not BAX, BAC, well, let's do BAC plus ACB plus CBA. Okay, so those measures sum to 180 degrees. So let's see where that leaves us. So if I move the measure of angle BAC to the right side of both equations, then the right sides of both equations are equivalent. So let me, if I did that, then I would know that the new left sides are also equivalent. So eliminating BAC, the measure of angle BAC from the left side, let me set what I would have on the left side, the leftovers equal to each other. So angle BAX is equal to, the measure of angle BAX is equal to the measure of angle ACB plus the measure of angle CBA. Now, the only way that the exterior angle measure can be equal to the sum of two angle measures is if that exterior angle is bigger than either of those angles. All right? So that's my proof that let me say it again. This is my proof that the exterior angles of a triangle are always bigger than the two non-adjacent interior angles. Okay? Let's do another example involving exterior angles and polygons. So what about a rectangle? So if you extended any side of a rectangle, what will be the measure of the exterior angle created? Can you see that you're always going to get a 90-degree angle? Okay. Now, I'd like to show you an interesting formula for the sums of the measures of the interior angles of any polygon. All right. You might know that the sums of the measures of the interior angles for a triangle are always 180 degrees. You might guess by looking at the picture that I just drew that the sums of the interior angles for a quadrilateral, for all quadrilaterals, is always 360 degrees. Okay? Now, it turns out that it's easy to calculate the sums of the measures of the interior angles for any polygon. Let me show you how. Suppose you wanted to calculate the sum of the measures of the interior angles for this pentagon. It might at first seem harder than it is, but let me show you a very nice way to do it. So imagine that you divided this pentagon into triangles. All right? Now, every pentagon, if you draw several of them, you will notice that you'll always divide them into 3 triangles. And we already know what the sums of the measures of the interior angles of all triangles is, right? So for a pentagon, you will have 3 triangles, so 3 times the sum for triangles, which is 180 degrees, okay? So what will you have? 300 plus 270 plus 240, so 540 degrees, okay? Every pentagon will have that for the sum, all right? Isn't that interesting? Now, if you didn't know what I previously said, which was that the interior angles of a quadrilateral the measures always add up to 360, you can quickly work it out. Let's draw any quadrilateral. Let's split it into 2 triangles. And then let's ask ourselves, what's double the sum for either triangle? Well, so that would be 2 times 180 degrees, right, which would give us 360 degrees. Okay? Now, I'd like you to do 2 exercises for me. What is the sum of the measures of the interior angles for a 12-gon? All right, and then what is the sum of the measures of the interior angles for an n-gon, where n is equal to a number such as 3, 4, 5, on and on. Okay? You may want to do the second one before the first one. All right? So pause the video and try to answer those questions now. Okay, so analyzing the results that we had so far, so a triangle, that's a three-sided polygon. A three-sided polygon was composed of one triangle. A four-sided polygon, in other words, a quadrilateral, was composed of two triangles. The pentagon, five-sided polygon, was composed of three triangles. So convince yourself that an n-sided polygon, an n-gon, has n minus 2 triangles. It can be divided into n minus 2 triangles. Therefore, the formula for the second question is 180 degrees times n minus 2. Okay? And so now we can handle the 12-gon without even having to draw a picture. So 180 times 12 minus 2, that gives 1,800 degrees. All right? Now, let me show you an interesting property of exterior angles. So it's going to turn out that the sums of the measures of all the exterior angles for any polygon will always, the measures of the exterior angles will always sum to 360 degrees. Okay? You can see that that's true for some simple examples like an equilateral triangle or a rectangle. Okay? Let me show you how you would prove that it's true in the general case. So suppose you had a polygon with n sides. Okay, then it will have n interior angles. Okay, and we know that the sum of the measures of the interior angles, we have a formula for that now. Let's say that the angles were labeled with a capital A, capital B, capital C, and so on. So the measure of angle A plus the measure of angle B plus the measure of angle C, on and on, etc. That's going to equal 180 degrees times n minus 2. Okay? Now, would you agree that every external angle has a measure that's 180 degrees minus the adjacent internal angle? Okay? So the sum of all the exterior angles, the sum of the measures of all the exterior angles is going to be as follows. So the exterior angle measure with respect to adjacent to angle A is going to be the following. 180 degrees minus the measure of angle A, right? And then the exterior angle measure with respect adjacent to angle B, that's going to be 180 degrees minus the measure of angle B. Okay, and I keep going on. And so that's the sum that we are trying to investigate. So how many of those exterior angle measures am I going to have? Well, I'm going to have n of those. Okay, so that means I'm going to have n 180 degrees, 180 degree angle measures added together. So 180 degrees times n. And then I'm also going to be subtracting the sum of all the interior angles. Well, we already know what the sum of the measures of the interior angles is. I just wrote it on the board. All right, and so we can expand and simplify. 180 degrees times n minus 180 degrees times n plus 2 times 180 degrees, or 360. So we get cancellation, and lo and behold, for every polygon, you'll always have that the sums of the measures of the exterior angles will be 360 degrees. All right.